there, y'all. Today we're going to look at 2.1 on arithmetic sequences. We're starting a new unit, and this is on analyzing exponential models. And so we're actually going to start with something that's not exponential and talking about arithmetic sequences. And then we'll get into things that are exponential again with 2.2 on geometric sequences and 2.3 and 2.4 looking at comparing exponential and linear models. And so we're going to start here in 2.1 on arithmetic sequences. And so in this lesson, the objective is that you'll be able to find a particular term of an arithmetic sequence. You'll be able to write arithmetic sequences explicitly and be able to write them recursively. And that actually falls under 4 different standards that we're going to be able to use here, being able to write arithmetic sequences recursively and explicitly. Writing a function that models the relationship between two quantities, and again, both explicit and recursive. You see a theme here with these. FIF3, defining functions recursively and recognize that sequences are functions, sometimes defined recursively. And then finally, FOQE2, creating symbolic representations of linear and exponential functions, including arithmetic and geometric sequences, given graphs and verbal descriptions and tables. We're going to mostly look at the verbal descriptions and tables for this section, and we'll deal with graphs as we go a little bit further along. So let's go ahead and look at some definitions that we need to know for this section. So the first definition we need to know is, what is a sequence? And so a sequence is a list of numbers or terms that have a logical pattern to them. And so we have a few sequences out there that don't have a pattern that we're going to talk about, like arithmetic or geometric, but there's a famous sequence called the Fibonacci sequence. And that sequence actually goes 1, 1, 2, 3, 5, 8, and so on. And this sequence has a pattern that is defined recursively. And we can talk about how we go from one term to the next using that recursive pattern. The arithmetic sequence, this definition here, is a sequence of numbers whose pattern is to add or subtract, because remember, subtraction is just the inverse of addition, by the same value between each term. So again, an arithmetic sequence is a sequence of numbers whose pattern is to add or subtract by the same value between each term. And so one more definition that we need to know is the common difference. When we talk about arithmetic sequences, the common difference is how I go from one term to the next. And so that's the numerical difference, D is the letter we'll use to represent that, between any two consecutive terms. And so we're going to look at some examples of how to identify arithmetic sequences, how to write them, how to find later terms, and so that's what we're going to look at in these examples today. So in example 1, we're going to determine if something is arithmetic or not. And so we said that to be arithmetic, the common difference has to be the same from one term to the next. And so when we look at a sequence like example A here, what we're looking for is, can I go from 4 to 9, and 9 to 14, and 14 to 19, and the pattern will be the same every time. So what does it take to go from 4 to 9? Well, we would do what? Add 5. And to go from 9 to 14, we're going to do what? Add 5. And from 14 to 19, we will also add 5. And so what we see here is a pattern that is adding the same thing every time. And so that means that it is arithmetic. So yes, it is arithmetic. And the second question says, if it's yes, that it's arithmetic, then we want to identify the common difference. Well, the common difference, our D, is just going to be this value, positive 5. Okay? So again, we want to look at how we go from one term to the next, and we want that pattern to be the same every time. We don't want it to change. We don't want it to go plus 5, and then plus 4, and then plus 7. That's not arithmetic. It's got to be the same value every time. So looking at example B, we have 2, 5, 9, 14. So let's look at this pattern. Well, 2 to 5 we add 3. And 5 to 9 we add 4. And 9 to 14 we add 5. So there is a pattern there, right? We go plus 3 and then plus 4 and then plus 5. And so we would assume the next thing is plus 6. But that doesn't make it arithmetic. Remember, to be arithmetic, all 3 of these and the whole pattern for the sequence would have to be the same value every time. And so this is not arithmetic. because our pattern is not the same between each term. Okay? And so let's look at example C here and see if we can see if this one's arithmetic or not. So in example C, we have 10, 7, 4, and 1. And so how do we go from one term to the next? Well, 10 minus 3 is 7, and 7 minus 3 is 4, and 4 minus 3 is 1. And so we have the same difference every time. And so yes, this is arithmetic. And so what is the common difference? What is our D? Well, it's this value of -3. And we have to have the sign with this because we're not adding 3 here. We're actually subtracting by 3 between each term. So we have to designate that with that negative. All right. So let's look at one more example here and see what the pattern's doing. And so in number 4, we look, well, 4 to 8 to 16 to 32. Well, this, we could look at one of two ways. We could see that, okay, we could go +4 and then +8 and then +16. So it's kind of like adding itself. Or we could also see that this is 4 times 2 is 8. And 8 times 2 is 16. And 16 times 2 is 32. And so, it's not adding or subtracting the same value to go between each term. It's actually multiplication. And so, is this arithmetic? No, it's not arithmetic. Because our pattern, again, is twofold. One, the addition pattern or subtraction pattern is not the same between each term. And two, it's actually a multiplication pattern. And so we're actually going to talk about multiplication patterns in section 2 when we talk about geometric sequences. All right, so that's example 1. Again, to be able to identify if something is arithmetic, we're looking for if the common difference is the same between each single term. Looking for that same plus the same value every time, or the same minus the same value every time. So let's go ahead and look at example 2. So in example 2, we're actually going to continue arithmetic sequences. So to do that, we've got to recognize the pattern and then continue the pattern. And so in the first example, we have 7, 11, 15, and 19. And so we want to ask ourselves, how do we go from one term to the next? Well, in this pattern, +4, +4, +4, right? So we're going to take the 19 and add 4. So 19 plus 4 is 23. And we would add 4 again. 23 plus 4 is what? 27. And then we can do 27 plus 4, which gives us 31. And so we can continue this pattern on forever, right? And so with arithmetic sequences, we're looking for that common difference to know how we go from one to the next. And we just continue that pattern. So let's look at example B. What happens here? Well, we go from 13 to 10. Well, that's going down, so we're subtracting 3. And 10 to 7, so that's -3. And 7 to 4 is -3. So we do have an arithmetic sequence here. And so what are the next 3 terms? Well, we're going to continue the pattern. 4 minus 3 is 1. And then 1 minus 3 is what? Well, 1 minus 3 would make it -2. And then 2 minus 3 is -5. So we see our terms there. All right, so let's look at one more pattern here. Let's try C. I want you to try this one on your own. So if you need to, pause the video for a second and look at this example of -9, -6, -3, and 0. So pause the video now and see this example. All right, so I hope you paused the video. I hope you try this one. Let's see if you got it right. So from -9 to -6, what are we doing? We are adding 3. We're going up. We're getting closer to 0, so we're adding here. And then from -6 to -3, you're adding 3. And from -3 to 0, you're adding 3. So this is arithmetic, and so we're going to continue that pattern. So 0 plus 3 is 3. 3 plus 3 is 6. And 6 plus 3 is 9. So we get those as our terms for this sequence. Again, it doesn't matter if the numbers are positive or negative. As long as we have that same common difference, we're going to be able to continue that pattern every time. All right, so we're going to go on to example 3 here in a second, and we're going to talk about explicit in example 3 and then recursive in example 4, how to write the pattern of these into an equation. So let's go ahead and look at those. So first off, we've got to look at this formula for the arithmetic sequences, and this is the explicit formula. So we're looking at how I can just look for the 1/1,000,000th term of a sequence if I wanted to. It doesn't matter what term we're looking for. This formula can be used to find it. And so the nth term of an arithmetic sequence can be found using this formula. It's a sub n, and that just stands for, the a is just our variable to stand for a sequence, and then the n stands for what term we're trying to find. A sub n is equal to a sub 1, so that's the first term, and so that's our word here. A sub 1 is the first term of the sequence. So a sub n is equal to a sub 1 plus d, and remember d stands for our what? Common difference. A sub n is equal to a sub 1 plus d times, we're going to use a parenthesis here, n minus 1. We have to subtract off 1 from the term we're trying to find. And the reason for that is when I plug in 1 here for the first term, that gives me 0. 0 times the common difference, so that's still 0, leaving the first term is equal to the first term. So when we plug in 1 for n, it verifies out that we get the first term back. Okay, so let's look at a couple examples on how to write the explicit rule from an arithmetic sequence. And then we're actually going to use that as well to find the 25th term, and that's what this notation says here. A sub 25 just means I want to find the 25th term of that sequence. I could write a sub 97, and that would mean I'm finding the 97th term of that sequence. And so we're always going to pay attention to what number is written here to know what term of the sequence we're trying to find. And just to clarify, that 25 or that 97 or whatever number of the term we're trying to find is not something we're going to be multiplying by to this a. It's not a coefficient or anything like that. It's not a power. And again, pay attention to how it's written. It's written as a subscript. It's below the line level of everything else attached to this variable. All right, so let's look at the first sequence. 7, 13, 19, 25. And so as we go from one term to the next, we're adding 6 here. And so we see our common pattern, our common difference, and so our d is equal to 6. But to write the explicit rule, we also need our first term. And so a sub 1, well, our first term is just the first number of the sequence. That's 7. And then we're going to be able to use our formula. So let's write that out. And so we've got a sub n is equal to a sub 1 plus d times n minus 1. And so writing the explicit formula, we're going to leave the n's in place and substitute in for the a sub 1 and the d. And so a sub n is equal to 7 plus 6 times n minus 1. And so this is the answer to this part of the question. Write the explicit rule for the nth term. Now, to be able to find the 25th term, we're just going to substitute in that 25 for a. And so everywhere I see, for n. And so everywhere I see n, I'm going to plug in the 25. So 7 plus 6 times 25 minus 1. And so a sub 25 is equal to 7 plus 6. 25 minus 1 is 24. And then 6 times 24, that's 144. So 144. And then we got to add 7 to that. So the 25th term of this sequence is 151. And so we could write out a sentence that the 25th term of this arithmetic sequence is 151. A lot of times we'll just leave it like this unless we need to use it in a different context. If we're trying to find what happens on day 25 of whatever's happening, right? So it could be what happens on day 25 when I make $6 a day, but I already had $7 in my bank account. We can see, oh, look, I have $151 in my bank account now. That's what arithmetic sequences can be used for. That's a good example of one. All right, so let's look at B. We've got a pattern here of 30, 26, 22, and 18. And so going from 30 to 26, we're subtracting 4. and 26 to 22, subtracting 4, and 22 to 18, subtracting 4. And so our common difference here is negative 4. Our first term, our a sub 1, is equal to our 30. Remember, our first term is just the first number in the sequence. And so let's write out the formula. A sub n is equal to a sub 1 plus d times n minus 1. And so we'll substitute the a sub 1 and the d, and so we'll get a sub n is equal to 30 plus negative 4, or we could just write minus 4 there in a moment, n minus 1, and we'll simplify that so that we see not a double sign here, but just minus 4 times n minus 1. And so again, this would be the explicit formula. And as we look for the 25th term of the sequence, we can substitute in the 25. And so a sub 25 is equal to 30 minus 4 times 25 minus 1. 25 minus 1 is 24. So a sub 25 is equal to 30 minus 4 times 24. A sub 25 is equal to 30. Negative 4 times 24, that's going to be negative 96. And so a sub 25, 30 minus 96, is negative 66. So the 25th term of this sequence is negative 66. All right? So with the explicit formula, again, we're able to find any term of the sequence that we want. We could be asked for multiple terms. We could ask for the 25th term, and the 50th term, and the 200th term, or whatever term we want anywhere, because it's going to give it to us every time. All right. So the last thing we're going to look at is example 4, and that is on recursive formulas. And the term recursive just means how do I go from one to the next, and one to the next, and one to the next. Recursive, another word there that we could use is a repeating formula. How does it go about itself? And so let's go ahead and look at example 4 and how we write the recursive form of arithmetic sequences. So to use the recursive formula, we're finding the next term of an arithmetic sequence using this formula. And so the formula is that a sub n is equal to a sub n minus 1. And what that notation means is I'm taking the term right before the term I'm looking for. So if I'm looking for the 10th term, I'm looking at the 9th term, and I'm going to add the common difference to it. And it's just like we looked at in example 2. How do I go from one term to the next to the next? And we can just keep repeating that formula on and on. Now, one thing we do have to know when we write the recursive formula is what is the first term. We have to know that the first term is equal to a certain value. And so the d, again, is the common difference, like we've used all through this section on arithmetic sequences. And a sub n minus 1 is the previous term. It's the term immediately preceding the one that we are looking for. So again, like I said, if we're looking for the 10th term, the previous term is the 9th term. All right, so let's look at the two examples here on how to write the recursive rule. And we're actually going to use the two sequences we used in example 3. And so we can kind of compare the two formulas as well when we talk about the explicit rule and the recursive rule. And so in example A, again, we've got 7, 13, 19, and 25. And so each time it's adding 6 to get to the next. And so again, we know that our common difference is 6. And the first term is 7. But to write this recursive rule, we're going to write a sub n is equal to a sub n minus 1 plus 6. And then we're going to put a semicolon and say that a sub 1 is equal to 7. We have to have that separate piece. Because if I don't put what the first term is, I could be describing any sequence where the common difference is 6. I could be talking about the pattern of 0, 6, 12, 18, 24, and so on. Or I could be talking about the pattern of 5, and then 11, and then 17, and so on. If we don't define what the first term is, the sequence could start anywhere. And it could even be a sequence that includes these values, but starts before 7 as its first value. We could talk about going backwards to like -5, and then 1, and then 7. But that's not the sequence that we have here. We have to define the first term. All right, so let's look at example B, the last example we've got here. And so in example B, again, we know the common difference because we did it on the previous problem. We are subtracting 4 from each term. And so our D is equal to negative 4. And our first term is 30. And so to write the recursive formula, A sub n is equal to A sub n minus 1 plus D. And the only thing that gets replaced in the recursive formula is the D. And so it's plus negative 4, or we could rewrite it so that it's minus 4. This is the recursive formula. And remember, we also need what? We also need to have the first term. A sub 1 is equal to 30. We need all of this information to write it recursively. All right, so that's the end of this lesson. If you've got any questions, remember to put them into the Canvas lesson check and make sure you fill out the Canvas lesson check and answer all the questions there. If you've got any questions, we'll talk about them in class, and I'll see y'all next time.